Alright, hello and welcome back to Passing College Level Chemistry. In this video, we are continuing the Chemical Kinetics mini-series and we will be discussing rate laws. So we'll start off by just defining what a rate law is, and why it's important. In the previous videos, we have seen how we can find the rate of a reaction and how concentration is a major factor in doing that. We know that the rate of the reaction depends on the concentration of one or more reactants. So let's consider just a generic equation where our reactant A decomposes into its products. Now, as long as the reverse reaction occurs at a significantly slower rate, we can write a relationship, which we refer to as a rate law. And that's just relating the rate of the reaction and the concentration of the reactant or reactants. I'm going to write just the general format in red. All right, and we'll go ahead and we'll define what each of these terms are. So rate we know, that's just the rate of the reaction. It'll have units of molarity per second. K we refer to as our proportionality, or more commonly the rate constant. And its role in this equation is to take into account time. We'll see how that is, why it's important in a few moments. A is just as it looks, it's going to be the concentration of our reactant A. And then N we refer to as our reaction order. The reaction order is not obtained from a balanced chemical equation. Actually, this is determined experimentally. So in an experiment, and we'll do an example at the end where we actually calculate this and see how that works. But this will be determined experimentally. If you have more than one reactant, if we had a reaction where we had A plus B to form products, we would write our rate law similar. We would still have K, we'd still have that rate constant. We would have A raised to the n power. Each reactant has a specific reaction order. So reactant A would have n reaction order. And then we would multiply that by reactant B, which will have its own reaction order. And I'm just going to abbreviate it as M. N and M may or may not be the same number. Each reactant has its own unique reaction order. So I'm going to write that over here. These may be the same number, these may not be, but we will do examples where we see that. All right, so a little more into reaction orders. Again, this would be N in our rate law. I'm going to just stick to that first equation that we had, where A decomposes into products. There we go. All right, so these three, N equals 0, N equals 1, and N equals 2, these are our most common reaction orders. They are not exclusively the only reaction orders you may see. You could see them with higher numbers or even fractions, but in general chemistry, these are the most common ones that we will come across. If you have a reaction order of 0, we refer to this as zero order. No fancy names here. And what this is saying is that our rate is independent of the concentration. And once again, I abbreviate concentration just with brackets but they're analogous to each other. So I'm going to say rate is independent of the concentration of the reactant. And if we were to write, if we were saying that in this example that A was found to have a reaction order of 0, we would say our rate equals the rate constant times the concentration of A raised to the 0 power. Now, whenever you have something raised to the 0 power, it equals 1. So I'm just going to kind of cross that out. Really, our rate will come to be equal to just K, just that proportionality constant. If we had an N equals 1, this would be first order. And not any fancy names here. This is saying that the rate is directly proportional. This symbol is a proportionality symbol. I'll say proportional in quotes. So this is saying that the rate is directly proportional to the concentration of the reactant. And if we were writing our rate law for this, we would say rate equals K times A raised to the first power, which is just A. Okay. And lastly, if we had an N equals 2, our reaction order we would refer to as second order. This is saying that our rate is proportional to the square of the concentration of A, or our reactant. And if we were writing a rate law for this, we would say rate equals K times A raised to the second power. So all pretty straightforward, but understanding what each order means will help us when we do examples and are looking at this. You can also see a question maybe on a quiz or an exam where they ask for the overall reaction order. And this is just the sum of the exponents in a given rate law. If we went back to that example on the previous slide where I had A plus B, two products, and we found in our experiment that our rate law for this was K times A to the first power times B to the second power, we would say that our overall order is just the sum of those exponents. So 1 plus 2, our overall reaction order is 3. That would be our answer. It's just the sum of the exponents. All right, now we'll do a little example of how to find the rate law, reaction order, and the rate constant. When we're normally determining the rate, we use a method called the method of initial rates. These are experiments that you would conduct in a lab where you vary the initial concentration of a reactant and you see what effect this has on the overall rate. So we would, like for example, what does doubling the concentration have? Like what effect does that have on the rate? If you have multiple reactants, like A plus B reacts to form products, you'll have to vary each reactant separately or independently while holding the other constant. That way you can see exactly what type of effect it's having on the reactant you're looking at. So what I did here is I made a little table. We have our reaction A to products, and I have these are each row is an experiment. So we have experiment 1 here, experiment 2, and experiment 3, or trial 1, 2, and 3, however you like to look at it. And these are not all done at the same time. This would really be maybe 9 experiments. I have the initial rate divided into 3 separate columns. It'll each be indicative of a specific reaction order and how we would find that. If we are looking at this second column right here, if we look at the left column, we see that as we're doubling that concentration of A, as it goes from 0.10 molarity to 0.20 molarity, our rate is remaining constant. And if we remember from the previous slide, if we have something that is, if our rate is independent of our concentration, then we have a reaction order of 0. So N in this case would equal 0 because the rate is staying constant. If we look at the second column right here, under the initial rate, or the third column, we can look and see as we double the concentration of reactant A, our initial rate is also doubling. So these would be proportional. As we double one thing, the other is doubling. Let's say as A doubles, rate doubles, which means that rate is directly proportional to the concentration of A. This would be indicative of a reaction order of 1. And then lastly, this final column here, this might sometimes be difficult to see. These numbers are pretty nice that we have. We can see that as our concentration of reactant A is doubling, our rate is actually quadrupling. And that is indicative of a reaction order of 2. I can just say as the rate is quadrupling. If we wanted to find this K value, again, that's taking into account our time. Once we determine what the reaction order is, if we were looking at our data and maybe we were looking at this middle column here, I'm going to put brackets around it. If we were looking at this middle column and we saw that, okay, this is a first order reaction, so I'm going to have the overall rate law look something like this. Trying to find what K is. Since I know my rate and I know my concentration, I can pick a row. I'll go ahead and look at this first row. I'm going to highlight the row that I'm looking at. I'm looking at this value and this value. Alright, and I'm just going to plug that into my rate law. My rate is 0.015 molarity per second. That is going to be equal to K, which is what we're trying to find, times A, which is 0.10 molarity. Since it's raised to the first power, it's just going to essentially equal this. I can now rearrange the equation and solve for K. No matter which experiment you choose, K will come out to be the same number, and we can check this. I will do a check to show that this is true. I'm going to solve for K, so what I'm going to do to isolate it is divide both sides by that 0.10 molarity. Look like this. When I do that, my molarities cancel, and the answer will be 0.15 inverse seconds. And that is where that time is taken into account. If I wanted to check this, I could, and we'll do that. I want to make sure that K is indeed 0.15 inverse seconds. I can solve for a rate, maybe by plugging in the concentration of experiment 2. 5 inverse seconds. If I multiply that by 0.20 molarity, will my rate come out to be 0.030 molarity per second? It will. So we know that this is indeed our proportionality constant. And doing so gives us the proper units. We know that we are in terms of molarity to the first order, so we only have one molarity. We had a second order, that exponent would distribute to the molarity, and we would have to have a rate constant that kind of balances it out so that our rate always comes out to be in units of molarity per second. So it's kind of cool to see. I'm going to go ahead and erase these annotations, and then we'll look at how we would solve for a reaction order. Alright, so now we are going to try to find what n is and how we would do that in a question. Usually we would do this if we're unsure about how the initial rate is changing with the initial reactant concentration, or if the numbers aren't as clear. They're pretty clear here, but if they weren't, if they were a little messier, we can substitute any two initial concentrations and their corresponding rates into a ratio of the rate laws to determine the reaction order. And the equation that we will use for that, I'll put in red. I'm going to put that up here over in the left. These subscripts right here, the 2 and the 1, they are corresponding to the rates. So if we were looking at, we'll do these two experiments, maybe our column right here, we have trouble seeing that this is a second order reaction where we want to double check. We can compare that. I'm going to look at, this would be my first experiment, this will be my second experiment. And so what I'll do, I'll just plug in my rates. My rates I see are 0.240 molarity per second divided by 0.060 molarity per second. And those are going to be equal to K times the concentration of, this is A, the second concentration of A, so that'll be 0.40 molarity raised to the n power divided by K of the first times the first concentration raised to the n power. Now in this equation, a few things are going to cancel out. I'm just going to cancel them out in a different color. Our molarities per second will cancel out. Our K's are going to cancel out. And our molarities are going to cancel out. They both appear in the numerator and the denominator. So first off, I'm just going to knock all those out. So you do not have to know K to determine the reaction order. If you know it, that's great, but you don't have to because they do cancel out. And now I'm just going to simplify. On this left side of the equation, 0.240 divided by 0.060 comes out to be 4.0. On the right side of the equation, both of these values are raised to the same exponent n, and they're being divided by each other. So I can go ahead and rewrite this actually just as a fraction in parentheses, raising that whole fraction to the n power. If I simplify what's in parentheses, 0.40 divided by 0.20 equals 2. That's still being raised to the n power. And I'm just going to rewrite this below. I'm going to drop the parentheses. Now, if these were different numbers, here it's a little easy. We can see if n equaled 2, then we would get 4. But if these were different numbers, if they were a little uglier, maybe they had a lot of decimals behind them, we can take the log of both sides and go from there. So the next step would be to use logs. And if you recall, I don't remember what math class this was in, but I think it was either an algebra class or maybe a trigonometry class. If you have a log of something, I'm just going to use a generic x to the a exponent, we can rewrite this as a times log of x. That's just a little trick. Refreshing up maybe a little bit just on the properties of logs might be a good idea if you're a little rusty with this. But to solve these problems, all you need to know is that you can do this with logarithms. So the next step that I would do is rewrite this as log of 4 equals n times log of 2. We now have isolated n, so yay, we can solve for that. I'm going to isolate it on that side of the equation by dividing both sides by the log of 2. I'm going to go ahead and just move over here. Doing that, I would get log of 4 divided by the log of 2. And if you go ahead and enter that into your calculator, you will see that the answer comes out to be 2. This is saying that we have a second order reaction, and our rate would be equal to K times concentration of A raised to the second power. So we just found this piece. But yeah, that is it. In the next video, we'll do a couple more examples. Again, if you have any questions, please leave them in the comment section. Thanks for watching.